In this video, we will talk about the continuous conditional distribution. Let's recall the basic idea of conditional probability first. The conditional probability of the event A on the condition B is defined as the quotient between the probability of A intersecting B over the probability of B. We use the Venn diagram to illustrate this idea. Basically, the conditional probability of A on B is talking about how much A is contained in the event B. Let's move on to our main objective. To motivate the definition of conditional probability density function, we adopt the infinitesimal approach. Let's fix the notation first. Suppose that capital X and capital Y have a joint probability density function denoted by f of x comma y. The following infinitesimal probabilities can be expressed in terms of the joint density function and the marginal density function as f of x comma y dx dy divided by f sub capital Y of y dy, where f sub capital Y is the marginal density function with respect to the variable capital Y. Therefore, the conditional probability density of x given y is defined by simply f of x comma y divided by f sub capital Y of y. And we're going to denote this function as f sub x on y of x on y. Following this track, the conditional probability of x in the event A given the value of y is simply the integral of the conditional density function with respect to x. Let's work on some examples. In the first example, the joint density function of capital X and Y is given by the function 12 over 5 times x times 2 minus x minus y when both x and y are in between 0 and 1, and 0 anywhere else. What we're going to do is going to compute the conditional density of capital X given that capital Y is equals to y, where y is in between 0 and 1. To kick off the computation, we're going to find the marginal density function with respect to capital Y first, which is by definition the integral of the joint density function with respect to x. And for our concrete function, the joint density function is only non-zero in between 0 and 1, so we can limit our integration region on this interval and take the integral with respect to x. The antiderivative is just given by 12 over 5 times x squared minus x cubed divided by 3 minus y times x squared over 2. We conclude that the marginal density function is just this expression. Once we have the marginal density function, we could go ahead to form the conditional density. Since this function is only non-zero in some region, let's specify that x is in between 0 and 1, and y is in between 0 and 1 as well. Then the conditional density function of x on y is going to be simply the quotient between these two expressions. And this completes our first example.